Okay. All right. So
Agent,
okay.
disease.
Yeah. So I don't know. Jesse said he might not be able to show up. He was going to do a paper presentation, but he had some things come up, so he might not be able to make it. If he comes in, he won't be presenting, but he still might be here. So, but we'll just go ahead with the two of you, and then we'll kind of go through progress. And so first, Stefan, you said you were having problems this week.
Yeah, exactly. So basically, I've kind of finished the simulation and the world visualization. The only issue I'm getting is that, sensors, I still have to work at sensor. There's some bug that rotates sensors not quite the way they should be rotated. So basically, I'm using this formula to calculate new coordinates of sensors based on rotation angle of the vehicle, but somehow they are moving, instead of moving around in a perfect circle, they start to move around in some oval shaped form, and no, even more like form of 8.
Oh.
And so that's the issue I will be working on probably next week or the week after the next week, to fix it so that it looks quite fine. But otherwise, it's totally fine. So, they don't escape the world anymore. They stay in limits. I've added wall propulsion this week. So, from the physics points of view, they move as they should. Yes, but then again, I've started to code off the neural network.
Okay.
And now that's of course not that easy anymore as it was with the world. So the basic code of network, I guess I should rewrite it a little bit. It's came out to be not that flexible as I would like it to be, so I'll do some refactoring on that. Yeah, and the problem is to do this refactoring, to modularize and abstract it in a perfect way. I should, of course, also have at least some idea how we are going to present it in a binary form and how we are going to, to maybe add some nodes there. So the most questions are with binary representation of the network and the algorithm according to which we would like to construct this network.
Yeah.
Yeah. And I guess there's some scientific discussion of this problem to be done. I've also posted it as an issue on our GitHub.
Okay.
Yeah.
Yeah, we'll go over that. Thank you for setting up a Trello board, too. I got that. So, I mean, is that just like sub issues and things like that? I was looking at some of the issues on it. So.
Mm-hmm.
Okay.
Yes.
So, yeah, for Ziyi's benefit, Stefan set up a Trello board for his just the stuff that he's doing, like sort of as he's walking through the project. I don't know if that's of any use to you, but yeah, it looks like it's. So I mean, that's just something you can do if you want. Yeah. So do you need me to?
Trello,
oh, is that?
So is Trello it seems like the same board as we are using in GitHub, right?
Yeah.
I don't know. Yeah.
Yeah, it's just an option, but yeah, I mean,
okay.
Are you, Stefan? Are you keeping like up to date with are you between our board and the Trello board, or?
You mean the GitHub board now?
Or the GitHub board? I'm sorry. Yeah.
Yeah. Well, I thought of them to be complementary. So for me, I don't know. In my vision, GitHub board is more like something that we group to, and my Trello board is then specific to my project. That's how I thought about it.
Yeah. Yeah. Okay. I mean, just as long as I guess more organization is better, not less.
Mm-hmm.
Well, we'll see how hard it is, how much time it takes, but it's. So yeah. So you were talking about instructables. So what does that mean? Like, what do you need for those next steps?
Sorry, was it a question?
Instructing the vehicles. What are the next steps on that?
Sorry?
Oh,
yeah. The signal, right? Can you repeat that?
Oh, I was talking to Stefan about instructables.
Oh.
Yeah. So, what are the next steps on that for the vehicles?
The next steps for the vehicles. I'm sorry. Was it some issue that I posted that you referred to?
I think so. I know. No, just in general, even like.
In general, yeah, exactly. So the next steps for the vehicles is the brain model, and the set. I would say the next step would be to define the form of the binary representation.
Okay.
And the form of constant networks. So basically, my thought is to go according to a paper of Kitano 1990, where he presents a method of constructing the networks, the graphs according to grammar rules, right? So this way, it's just in this case, it's for me the only possible method because we have to represent different size networks in a bit string of some defined length. And if we would do it, so basically the approach with adjacency matrices as they are directly, it would be not that scalable, and it would be quite hard, to. So if we have some really small network and some really big one with many nodes, they will have really different length bit strings. That's the problem. If we would just convert adjacency matrix to a string. So what this grammar rule approach potentially does provide us is the way to at least make bit string lengths for different size networks at least somewhat equal in length. First, and second, also to make the construction of network scalable so that we can construct networks of 20 nodes or 40 nodes without giving this 40 times to square overhead of the calculations. And the problem there, I was reading yesterday this article. I mean, I get the general idea, but then it's still quite hard to define how we would implement it in our case, right? Because it's kind of the basic idea of this grammar rule approach is that we have some grammar rules that basically define some connectivity patterns at the very end, some connectivity patterns in the networks. And so the question really is, do we know these patterns beforehand, before we construct the network, or what would be initial, so to say, what would be initial grammar rules? So what connectivity patterns would be reasonable for our case?
Okay.
I guess. And also I should read a little bit more into this approach because I don't understand it to the extent where I can implement. Yeah. So that's basically the issue. I guess that's the thing that matters the most now.
Okay. Well, that sounds good. Do you have a citation for that paper you can share? Or
yeah, sure. I will
just put it
share
in the
it right away.
chat, and then we'll look at it. And Ziyi, do you have any comments about that, about his approach, or maybe any suggestions?
No, sorry.
Okay.
Yeah.
Okay, yeah, so share that citation, and then Ziyi, I want to ask you the same question. Like, what are the things that you've been working on the last couple of weeks that you have issues with or need to discuss?
Yeah, so I was confusing about the network structure, and I was reading papers, and I found a very nice paper, and so it's basically designed a structure called the Hopford network. So that was designed for olfactory bulb, and so basically it's very much like the Hopford network, except that neurons that are like far away from each other are not connected. So the network basically is like an simulation of the olfactory bulb involving two types of cells, and it's very nice. I basically made a model, so
Okay.
I mean a simulation. I'm going to share my screen.
All right.
Can you see it?
Yeah, I can see it.
Yeah, so model is basically when the relative, like I said, when relative channels, when say the value of inputs is like increasing, it's gonna be gives output to the brain like over time. But if like the inputs is not like some channels of the inputs are not changing, or the changes are very small, then it's gonna just go down and do not give us any output. So it's just like two layers. There's the first layer, then the second layers. And so in the brain, the first layer is the mitral cells, and the mitral cells give output to the brain, to the cortex, and the granule cells are basically the inhibitors of the mitral cells. So that is a simulation of the olfactory bulb, and I think I'm going to use it as any part of the olfactory system. And I'm also currently reading papers about the gas category, and it seems like there are not so many models of the gas category system than the olfactory system, so I don't know. And for the neural comparators, also there are not so many models for neural comparators, and I think the one you provided is very nice. And I'm thinking about how can I like combine the model, combine the Li-Hao network and the neural comparator, as well as the gas category system I'm going to build.
Yeah, that was, you asked me about that in Slack, and we discussed it a little bit. And I pointed you to some papers on. It's basically the idea of neural coding. So there's a whole literature on that, and I don't want you to get lost in that, but just I think you've picked a couple of examples that are, pretty close to what you want to do. And then I guess we'll just see if they implement well. And so that looks good. You have some good results, actually. So thanks for sharing that. Any thoughts about next steps? What in the next week or two, what you might want to accomplish?
Yeah. So in next week, I'm going to firstly test more on the simplified model I built for Li-Hao network. So to just make sure that SLA produce some sort of meaningful results for more complex environments. So basically, I was simulating for input of as a vector of 10 elements, and only one of the elements are increasing. So for my environments, there will be more. So yeah, I'm firstly going to test it, and I think that will take just for say 1 day or two. And also to study more about neural comparator and to see if how can I combine it. Yeah.
Okay. So you're combining sensory inputs, like from different sensory systems, or are you still at like just combining sort of like stimulus? It's I'm not quite clear on. Is it like combining like sensory input, like sensory modalities, or is it in integrating inputs? Like you have these two different models for.
Yeah, so basically the model, the Lee helpful network can give outputs that magnifies the changes and ignore the parts that does not change. And I think that is a very nice behavior. And that's also mimic the real the real O-factor system. And I think I'm going to use neural comparator in a way that can say, yeah, I have to think about it.
Okay. Well, I mean, yeah, start like, the idea would be, I guess, if you had different. And when I was reading your proposal, I was thinking about it this way, where you would have, a couple of sensory modalities, like you would have, olfaction and gustation, and then you could combine, you could use those as sort of their separate streams of information to tell you different things about the environment, but you could also combine them downstream in terms of like producing something that's sort of a combined signal. And I don't know how hard or easy that would be, but that's the idea that I kind of had about like how that might work or how that might, translate into the nervous system. I don't know, once you start working on the network, so they're different. They're different networks, or they're basically the same network, but they take in different inputs, or how does that work?
Sorry, the Wi-Fi here is not good. Are you asking about what's the difference between the Hopfield and the Hopfield?
Well, I mean, like for the different modality, like different sensory modalities, like gustation versus olfaction, are those two different networks, or are those on the same network, and they just process different?
It's very similar to Hopfield network. So in olfactory bulb, the mitral cells are on the outer surface of the bulb, so it's just like the sophia, and the granule cells are in the inner surface of the bulb. So the Lee-Hopfield network basically is like neurons that are nearer to each other are connected. If they are far away from each other, then they are not. So they're kind of like Hopfield network, but neurons that are very far away from each other are not connected.
Okay.
So in the original paper, there are. I can share the paper. There are mathematical analysis of its behavior. So it basically behaves like a damped oscillator.
Okay.
Yeah, I can share the paper.
Okay, that'd be good.
And here is another one.
Okay. Okay.
And I use and I use Hebbian update tool for finding the better connection matrix of the Lee-Hopfield network. Yeah, so.
Okay. Well, I mean, that looks good. So yeah, I guess keep working on it. I guess the question I had, which I didn't really form very well, was I'll save it for later, because I think at this point I want to get all this nailed down first. Well, I guess I was asking about like So if you have if you have a Hopefield network, it's processing. You have gustation and olfaction. It's two different sensory inputs. Is it using the same Hopefield network, or are they using different Hopefield networks for each sensory input? Or is it just where they're comparing the inputs of the different things and then comparing those, like comparing olfaction and gustation? That's what I'm not getting.
Sorry, can you say that again?
Okay.
The
connection is a little iffy. But so when you have your two sensory inputs, olfaction and gustation, are you using the same network to evaluate them, or are you using different networks?
So for olfaction, I'm using this Hopefield network for, say, the in-nest connection. But for the gas detector, I think I guess I'm currently still writing a paper for the models. I guess the gas detector is going to be simpler and easier. I don't know, in terms of my biological knowledge, but I don't know currently. There are not so many models for the gas detector system.
Yeah, olfaction is really combinatorially hard because you have so many different odorants that you have to sort through. I mean, in the biology of it. And then some organisms are very good at finding the right odors, but it's it's a really hard problem in terms of there's so many different possible combinations of odors that can be processed by the bulb, and so some animals have really big olfactory bulbs, others have smaller ones, and that's related to their ability to pick up different types of odors. And then I guess in the gustatory system, it's a bit less complex, but I'm not really sure about the state of the art about models there. So, well, that's good. I guess we'll see when you get to the point of having each sensory type represented. Then the next step after that would be to go to to translate that into a integrated system where you would use both modes of information, or
So the Hopefield network will asking I'm going to use which kind of model?
Just when you have the two different types of sensory input, would those be combined at some point, or would they be work separately in the? Would you just have them separately and take that information?
They will be separated.
Okay. Okay, well that's good. I mean, I think you got a good start on that. I'm glad we got the.
Sorry about that.
It's okay. I'm glad we got that sorted out, from the conversation on, I guess, Friday or whenever it was, or Thursday. So good. I look forward to seeing. Let's keep doing these kind of updates where you show a little bit of what you're working on, and we'll. Stefan, do you have anything to say about it, or do you have any comments?
It was just, I have a question. What is a neural comparator? Didn't quite get this. So you mentioned that you're using some neural comparators in your model. Yeah, and I was wondering just.
So a neural comparator is it's just
better said,
how
better said,
sorry?
what were you using for? What do you using neural comparators for in your project? Just like the use case of it. Didn't quite get that.
Oh yeah. So neural comparator is like a network that takes two kinds of inputs, and you sort of indicators about their similarities.
Oh, okay. So it's a separate network that will compare two types of inputs and provide you with information about this comparison. You get it? Okay, thank you.
Is that?
Yeah.
Is that all you? Yeah. Okay. So, well, that's good. Thank you for sharing, both of you. And now we'll move on to the board, just to see where we are on that. So let me put the board in the chat, so we remember where it is. All right. There's the link. And if we go to the projects tab, and we go to the link there, group meetings review, that's the board. And we have all of our issues here, which are starting to grow here a bit. We have done, in progress, and to do. So let's start in done and work our way backwards once again. So we've got exchange proposals, that's been done. Get in touch with SimBrain developers, that's been done. Work on presentations, so Ziyi is going to present next week on the paper that you proposed. You still plan on presenting that? Any problems or issues with that?
Yeah.
Okay.
I can present.
Okay, good. And then we have to reschedule Jesse's presentation. He'll probably present the week after that, but we're working on that still. Okay, the documentation of the Jupyter notebooks. I'm glad to see that Ziyi has a Jupyter notebook that he just showed us. So congratulations. Then we have set up presentation schedule, that's done, and set up programming environments, that's done. So present papers, that's kind of in progress. Share resources and implementation ideas, that's in progress. And then I created 18 create Trello board with tasks. So that was for Stefan, and it looks like you've done that, and we discussed that already.
Yeah.
So, and then so can we think of any other issues we want to put in the in progress tab? Or just to create new issues?
Yeah, I would say we can put number 16 to the in progress.
I'll pick initial
because
board
I
link,
will be, yeah, exactly, yeah.
Okay. And I'll probably, well, I could put Ziyi on that as well, just because it seems like he's right kind of where you are, but kind of coming at it from a little bit different direction. So I'll assign both of you to that, and then that's in progress. So it looks like you guys are both kind of starting out to getting your networks firmed up and working, and now it's a matter of like refining and debugging. So we'll put that in progress. Any other issues maybe related to that, or maybe other things you can think of?
Not at the moment, no.
Okay.
May I ask what is conference funding?
Oh, okay. So this is Stefan is he submitted a tutorial to the INCF conference at in Warsaw, and so he's got it accepted. And there apparently in the GSOC program there's a $500 stipend for travel. And I just had to dig through like some like information about it online. So I don't really know anything about it other than that it somehow exists. And so, Stefan, I suggested that you contact Malin about it at INCF, or I can do that. Just, I don't know. She probably knows more about it than I do, so. But I'm pretty sure that exists. So, yeah. So, let's see. We'll put that in. Let me actually, did I assign it to? Yeah. So I'll put that in progress and then follow up on that. Find dataset references for GitHub repository. I think that's for me. And I haven't actually, there have been things being added to the repository. If you look in the different folders, I've added some information actually about the OpenWorm, what's going on in the OpenWorm Foundation. So as you may, both of you I think know, I work with the OpenWorm Foundation as well, and they do things with the C. elegans connectome. So their interest is in, modeling the C. elegans connectome, each cell in that connectome. And the thing is, with C. elegans, we know every cell in the connectome, and we know what it does. And so we have information on each neuron in that connectome and the connections between the cells. And so I'm going to be adding references to that. So if there's if there's an interest in it, people can use that as sort of a reference point to think about what a connectome looks like, like in a real organism where you have functional attributes and, the C. elegans, they're not exactly like, say, the human brain where we have, they don't really have, there's some debate as to whether they actually have action potentials. They do have electrical activity, but whether they're action potentials or not is a little bit in dispute. But in any case, it's a nervous system and it does things like, behave and, do other things. So it's that might be worth someone's time if they're interested. So I'm just going to put that actually in progress. So let's see. Research potential issues with building block method. This is for Stefan.
Yes, I guess I want to we can put this in progress, of course, but I would say firstly that maybe it can be built in later, at later stages of the project, but not that I would have time for this now, I would say.
Okay.
I guess the issue number 16 will take pretty much of my whole time for the next few weeks, or maybe the next week.
The 16. Oh yeah, that one. Yeah, that's probably.
Yes, with brain and network. Yeah.
Yeah, I think that's probably the first focus area, or at least the most important focus area. That's right.
Yeah, sure.
We want to prioritize everything, so it's you can't really do one before you do the other. But actually, yeah, I mean, so that's what was that?
I mean, when this is done, so when the binary conversion and network building methods are defined, and we are also we know how the binary represents the networks. It's basically just a matter of a few hours to code down the genetic algorithm itself. Because I've already done it, it's not that hard compared to what there isn't there with the network's representation.
Maybe I should ask you, when you say how to create a binary encoding, what are you thinking in that department? What do you?
So basically, in this case, if I would have some grammar, I would just maybe take, I would just map symbols that are there in the grammar on to some binary sequences of the same length, according to how many symbols we will have. So, for instance, if we have I don't know, letters of English alphabet. It would be 26 of them, and we would then let me see, 22 to represent 26. Where is so 64, 32 would be enough, and so it would be 2 to 5th. We would need 5 bits to represent. You know, to go down to the symbols.
Yeah. So you're just talking about representing things in binary, like you'll take in.
Yeah, exactly, and of course, we need also this mapping that would, when it's mutated, it would be mapped all the time. It would be mapped to the things that we have in the grammar. So that's also the main thing.
Yeah.
Like for instance, that we don't get any other characters that we don't have in the grammar. Yeah. That would be also a thing. So, for instance, as we see now, as I've said, we would represent 26 letters of English alphabet with 5 bits. That means that some numbers would be kind of redundant. Yeah, so exactly same. It would be 6 of them. So 6 numbers would be mapped either to nothing, or it's also possible that we do map, some common grammar rules or some rules that are more important than others to these redundant numbers. It's of course also, all of it should be defined and thought about, and once we have that, I mean, generic algorithm is not a thing anymore.
Yeah. But this is, of course, a very important step, because you need to have that sort of base, like it's like the floor to a house, right? So if it's hard to get a handle on, like if you can't encode all of your inputs, or that it doesn't make sense, that's going to be hard to. Well, I mean, I look forward to. So it sounds like it's like going to be a little harder than just throwing down a simple like mapping scheme. I mean, do you have something that you're going to use, like some sort of like set of rules, or like is there something that already exists that you can use, or how is this going to work?
Yeah, exactly. So I've basically copied over this link. I will share you this citation that I have, that I'm currently using the most, which I built upon at least. And I also can just send it there directly to the paper itself. It's here.
All right.
Yeah.
And so let's see, that's the link to the paper. All right. It's taking a while to load, but okay, there we go. Designing neural networks using genetic algorithms with graph generation system. So they're doing several reports. Scalability, convergence characteristic. Okay, so this is graph grammatical encoding. That will include graph generation grammar to the chromosome. Okay, so yeah, this is specific to a chromosome in a GA. Although you could use it you could use it just to generate a binary string for other purposes. It doesn't have to be, but yeah. And so do you think this is relatively easy to implement?
I don't think so, to be honest.
Yeah, I mean, I don't know. I mean, like,
it should be implemented, right?
Yeah.
So
implementable, yeah.
It's implementable, yeah.
Yeah.
That's,
well, yeah, I think you should really, maybe reserve a block of time for it, or maybe, maybe understand it a little, maybe make sure you understand it before you try to wade into it a little bit. Yeah, I mean, it looks good though. I mean, if it works, it'll be it'll be great. But I'm not really.
Yeah, I mean, it's also a pity that their code is not on GitHub, you know.
Oh yeah, it's 1990, so I don't
Yeah,
even
19.
know
It's a bit
what the
too early.
standard is here.
Yeah.
Actually, so they give like in Figure 2, they give a connectivity matrix, an actual network, chromosomal representation, which is I guess just taking that connectivity matrix and mapping it to a string, like a one-dimensional string instead of a matrix, or two-dimensional string, or one-dimensional string of two chromosomes. And then
They do even more than that. If you like look at their XOR network representation, they have kind of this grammar rules. So basically, what we have there is that we have various steps, various cycles, so to say, where we start to, so to say, roll out the network, right? So we have the initial state S over time, and S maps to A, B, C, D matrix, and so we have cycle 1, which is A, B, C, D, and then each of symbols A, B, C, and D, they map to the unique representation with smaller letters in this case, and then the smaller letters, they also kind of roll out to the end numbers.
okay, yeah, I see that in Figure 4. They kind of get
exactly, and so the basic idea of this, these symbols only make sense if they are shared across various networks. And if they are shared across various networks, that means that the symbols calls for some special patterns. So we would see, if we would see symbol B in various networks, it would mean that parts of all of these various networks, some part of it is totally the same. So it's shared multiple. Which in our case, I would say, intuitively, and what we also see biologically in animals, it's sensible. So it has reason. We really see some connectivity patterns, but then, of course, it's hard to define and hard to think about why would we make some pattern a motif and a grammar rule and not the other one.
right. Good. It's kind of back to like innateness, like what do we really know, like when we're born, or do we really know what a network looks like, before it's formed? Like, is it preformed? Like in the C. elegans example, the cells are, they differentiate and they end up and they're always in the same place, and they're always the same cell and they always have the same function. So a lot of insect nervous systems are like this too. You can go to any insect and you can find, given the species, specific cells that do specific things. You'll have like nuclei that do X. They have some certain function and they're connected in a certain way, and they're always connected that way. Whereas in the human brain, you have a lot more sort of flexibility. Neurons are sort of generic and they're connected, but they're not connected always in the same way. They just they're used for processing. So, that's a feature of nervous systems. And so, you say, well, what do we know, given that our brains are much more generic, say, than an insect brain? What's hard coded in there? That's maybe why we're so flexible in terms of language and in concept building. It's like that may be one reason why that is. Social insects like ants, they have a very hard-coded sort of, very exquisite social behaviors based on pheromones and things, but they're very hard-coded. And so, or at least we think they are. And so, that, I don't know, I mean, you're kind of unlocking that whole can of worms, but that's sort of the idea. And yeah, it'll be interesting to see how that works out.
Yeah.
So, Z, any thoughts about this, or? Any thoughts about the creating like a binary encoding?
Nope.
Okay. Well, I mean, it might be useful to you, but we'll see. Let's go back to the board real quick and kind of finish up. I added a issue, work on binary encoding, and I'm just including everyone on that so that, in case it's useful to someone, you can follow up on it. review components of model. So this is for Ziyi, and I think we're doing that now, at least internally. So, but we'll keep that in the to-do list for now. I think the suggestion was that we go a little bit more public on that. So, number 12 was to do review Holland's paradigm. That was it's probably for later, but that involves Jesse as well as Stefan. And then community evaluation, which was Stefan's idea. Again, that's kind of like similar to I think number 12, although I think I think reviewing the model, Ziyi's model at different stages is a pretty good idea. So we'll keep doing that. Any other issues before we go? Can you think of that we need to add to the board?
So yeah, on me it's fine that we added this issue.
So for next week, we're going to.
So it's fine that we added this work on binary encoding issue.
Okay.
I guess it's the most important one from you.
Okay. Ziyi, you said something I didn't catch. Oh, you said something. I didn't hear what you said.
Yeah. So for next week, are we going to meet like normal or like the time today?
Yeah, we'll meet on Saturday at the same time. So not Sunday. I had to move it because I was out of town and I couldn't make the Saturday. But we'll meet Saturday at the same time. And so then you can present. Okay. Okay. Anything else that we need to discuss before? Okay.
Not right now, no.
Okay. Well, thanks for meeting, and thanks for meeting on a different day. That was convenient. So if you have any other questions, please Slack me or email or whatever, and then we'll talk next week. Okay. Thanks.
Right.
Thanks a lot, guys. See you.
Thank you. Bye bye.
Have a good week. Bye.